Welcome. Using transformations of an exponential function to model a situation. A cup of water is heated to 100 degrees Celsius and then allowed to cool in a room with an air temperature of 20 degrees Celsius. The temperature T in degrees Celsius is measured every minute as a function of time m in minutes, and these points are plotted on a coordinate grid. It is found that the temperature of the water decreases exponentially at a rate of 25% every 5 minutes. A smooth curve is drawn through the points, resulting in the graph shown. A. What is the transformed exponential function in the form y equals a times c to the bx minus h power plus k that can be used to represent this situation? So let's break down all of the pieces of information we're given and use that to figure out the values that go in the equation. Right, so what really stands out to me is this statement right here. So the water decreases exponentially at a rate of 25% every 5 minutes. Gee, that's important, right? So that's going to be key to finding our base. Our base is the c in the equation, right? So c is our base. And for decay, to find the base, it is 1, because you start off with everything that you're starting off with, and then you lose stuff, right? Here we're losing temperature, right? If you ever made a cup of coffee or a cup of tea or a cup of hot chocolate, you know, it doesn't take very long before it's like, oh, this is too cold, right? So it gets cooler as it's just sitting around, right? It starts to match the temperature of the room. So to find our base, we're going to take 1 minus our rate of decrease. And our rate of decrease is 25%. So we have 1 minus 0.25, which is 0.75. Or let's write that as, we can write that as a fraction. You can write it as either 3/4 or 0.75. Actually, you know what? Since I don't have any more space over there, let's just keep it 0.75. All right, so now that would be our base if this said, no, don't do this. If this said every minute. So if there was no 5 there, 0.75 is, actually 0.75 is our base. But it would just be, our equation here would just be y equals, well, we'll have to figure out a. But 0.75, don't write this, to the b would be 1, right? So that b right here would be 1 if that said every minute. But it doesn't say every minute, so it's not 1. So don't write that down. I wrote that just so you would see why it's not 1. It's every 5 minutes. Right? Now, our equation is also not this, whatever a is, 0.75, 5 times x, whatever h is, all right, plus k. Our equation is also not that. What that would mean, so don't write that down, because that's not our equation. What that would mean is that the water temperature cools, it cools 25%. Right? The rate of decrease is 25% every 1/5 of a minute. Right? Because that's going, if we have 5 there, it's going to shrink our graph horizontally. I'm going to need a value 1/5 as much if I go and multiply it by 5. Right? So that is not our equation. That would be if it said that the water decreases exponentially at a rate of 25% every 1/5 of a minute, which would be every, what, 60 divided by 5, 12 seconds. So if it decreased every 12 seconds, 1/5 would be correct. So that is not our equation. So if it's not 5, it must be the reciprocal of 5. Right? So that means that B here is going to have to be 1/5, because remember our horizontal stretch is the reciprocal of our value, right? So if B is 1/5, it's going to take 5 minutes for it to cool, right? And we'll plug in a value so you can see, yep, it's going to be 1/5. But let's just write this as an easy equation. Don't write this part either. Let's just say we had y equals 2 to the 1/5 x, all right? And we wanted to figure out what we would have to raise. It's not a great number for 2, but what we would have to raise, I know, y to x, what would x have to be for y to be 32, all right? We want y to be 32. Well, I know 2 to the 5th is 32. So that means I'd have to raise it to the 25th power. Right? And so that would give me 32 equals 2 to the 5th, which is indeed correct. So you see, if I want a value that's 5 times as much, right, on the y, I'm going to need a value that's, I want b to be the reciprocal, 1/5 as much. Right? So if it tells you every 5 minutes, or every t minutes, let's just say if it says every t minutes, right, that b is going to be 1/t. And if it tells you every 1/t minutes, it means b is going to be t. That's the one that is always the reciprocal. All right, let's erase all of this because this has absolutely nothing to do with the problem, other than I want you to understand why b is 1/5, not 5. All right, so we've got our c, we've got our b. The k is really easy to find. K is your vertical shift. Well, the graph gives that away, right? We have a horizontal asymptote at y equals 20. That's our vertical shift. So that means k is 20. So that one you can just look at the graph and see it. You had to think, you had to do a little bit of solving to get the c, the base. You had to think, what does that mean every 5 minutes to get the b? But you just have to look at the graph to get the k. Now, all we have left is the h and the a. H, we can think about it intuitively, and then a we'll have to solve for. All right, so now if we look at our graph, notice where our graph starts. All right? It starts right at 0 minutes. Now, if you've ever made any hot beverage at all, you know that as soon as you're done cooking it and you put it in the cup and you start to drink it, it starts cooling down, right? It may be boiling hot when you make it, but right away it's going to start cooling down, right? So H is 0 minutes. Right away it's going to start cooling down. And we can also see that from our graph. Notice that the graph is not shifted horizontally. This is a real world problem, so our graph starts as soon as we finish heating up the water, right? Notice there's no negative numbers on our graph because that would imply negative time, right? We start at 0 minutes. So because we start at 0 minutes, our H is 0, right? So nobody says it can't just be 0. So now the only thing we need is the A. We have to solve for that, but we have all of the other pieces of information, right? So we have y equals A times, our C is 0.75 or 3/4. Since 0.75 is an exact answer, it doesn't matter. which one. And to test it, I'm going to plug it into a calculator anyway. And it's, because the numbers aren't going to be that pretty. And it's not going to matter whether it's 3/4 or 0.75. I plug into a calculator. Our B is 1/5. Our H was 0, so I can just put X. And then we have a vertical shift of 20 degrees. And we'll talk about what that 20 degrees, we'll talk about all of these features relative to this problem in part B. Right, because B is explaining how it relates to this real world problem, not just this as a graph. All right, so we have two variables there. Actually, we have three variables. We have y, a, and x. Right? A we don't know, but we could substitute a point for x and y. Right? And if you look at our graph, I mean, these aren't the prettiest values in the world. Right? Like, I don't know what most of those values are because I'd have to approximate them, except for one. I know this value. When no time goes by, that coffee is 100, or whatever it is, the water is 100 degrees. I rarely drink hot water, unless I turn it into tea. So I want to make it something. I want to make coffee or tea, I guess. All right, so we have a point. We're going to substitute 0 for x and 100 for y. So we have 100 equals a times 0.75, 1/5 to the 0 plus 20. All right, so 100. So we can, let's just simplify off as much as we can before we start moving things around. 100 equals a times, all right, so 1/5 times 0 is still 0. So this is 0.75 to the 0. We're solving for a, so we want to get a by itself. Let's subtract 20 from both sides. So we have 80 equals, but what is anything to the 0 power, right? That's just 1, right? This just equals 1. So I've got 80 equals 1a. So 80 is a. And now we have all of our pieces in this equation. We have the b, which was the coefficient on the exponent. And the only reason there was a coefficient is because they said every 5 minutes. If they had said that it decreases exponentially at a rate of 25% every minute, all right, then b would be 1. If they said it decreases 25% every 10 minutes, then b would be 1/10. If they said it decreases exponentially every 30 seconds, and our graph is in minutes, then b would be 2. Excuse me, I almost said 1/2. B would be 2. B would be 1/2 if it was every 2 minutes. Right? So it's going to be the reciprocal of how long it takes. Right? And our h is 0, so I'm not going to plug that in. Our k is 20, and that's everything. So our equation is, I'm putting it in a different color, is y equals 80 times 0.75. Oh, our base is our c. Sorry, I didn't box that one in. Our c is 0.75. All right, y is 80 times 0.75 to the 1/5 x plus 20. Now you might be thinking, why isn't our starting value 100? Right? Well, if our starting value would be 100 on our graph, it'd be, or why isn't a there 100 instead of 80 instead of 100? Well, if it had been, we've shifted our graph up 20. So if a is 100, that means on our graph it would be 120. Right? So our a is not the actual temperature of the coffee, right? It's the difference between the temperature of the coffee and the temperature of the room, because our whole graph is shifted up 20. Because it's never going to go, it's never going to get colder than the room, right? It's not going to, unless you put it in the refrigerator. All right, so let's actually check this out, and we'll use 20 because, well, why not? And if we get something, so here, let me move that down. We can't even see the number. Okay, so this is 50 right here, right? So if I get something that's a little closer to 50 than it is 40, it's probably correct. So if it's like somewhere in the middle of 40 and 50, maybe a little closer, it looks like it's going to be closer to 50, we can feel pretty comfortable with that. And we're going to use a calculator for this because, well, this would not be, this is not a do in your head kind of problem. All right, so we have, so we're plugging in, I should write it down. We're gonna, oops, there goes my calculator. This is gonna be our test point. So we're gonna test our equation and see if it's good. So we have y equals 80 times 0.75 times 1/5. We're plugging in x at 20 minutes. All right, so our x is 20 minutes. And our y should match our graph if this is correct, and then plus 20. All right, now let's plug that into a calculator. Now we all know what we're doing. All right, where'd the calculator go? There it goes. All right, so we can see both this and we can see both what we're plugging in and the calculator. Now this is a bit of a backwards calculator, so I have to be creative. And hopefully I do it right the first time. 0.75 raised to, all right, so I want it to, well, you know what? 1/5 of 20 is 4. So let's not put in 1/5 times 20 and then have to make sure we get that so the calculator understands we want the 4th power. Let's just do the 4th power and then equals, all right? Now we got to multiply that times 80. Sorry, this calculator works piece by piece. So what's in the calculator now is 0.75 to the 4th power. And 0.75 to the 1/5 times 20 power is 4, right? Because 20 divided by 5 is 4. All right, now times, I don't know if I hit times, times 80 equals, and then plus 20. All right, we are halfway between, and probably I thought it might be a little closer to, but I knew it was pretty close to halfway. Yeah, I guess it is really halfway. If my dot isn't giant, or maybe how is this? Yeah, I guess with my dot being so big, it's hard to tell exactly where it is. So let's make a smaller dot. So right here, I guess that looks like 45. That certainly seems quite reasonable now, doesn't it? So I feel pretty confident because we got y equals 45, about halfway, and a teensy-weensy bit closer, point something degrees, 0.3125. And that seems to fit our graph. Let's go through B here, which is our parameters, and what each of them means. All right, so we had A. Let's write our equation again, just so we remember where things were located. Y equals 80 times 0.75 times 1/5 x, and let's put minus 0, just because we do still have to talk about our h. So 1/5 x minus 0 plus 20. All right, and this is y equals a times, I think it's c to the b times x minus h plus k. All right, so now we can see what everything is. All right, so we'll just go right through, I guess. All right, so A is the difference in temperature in degrees Celsius between the water and the room. All right, B is actually, sorry, our next letter is C. It's not alphabetical. All right, C is, it's not our rate of decrease, it's not how much temperature we're losing, it's how much temperature we retain. What we lose, we subtract from 1, right? So the water retains 75% of its current temperature. And really, you can't talk about C without talking about B. So B, it goes with it. So let's just put them together. Every every 5 minutes. All right, so the B equals 1/5. That represents the interval of time actually, you know what? So I don't have to repeat myself. Let's just say of its current temperature. And then let's talk about B. All right, so B equals 1/5. Actually, let me also put in, well, I think with our little thing there. But I will put in B, because B is, I think, the trickiest one to find, right? Probably A and B. I think the others are a little bit easier. So I will put 80 there for A, just to make sure we knew. We've got the number in there for C. All right, so we're good. So B equals 1/5, which represents the interval of time which is 5 minutes, over which a decrease, oops, well, I guess I leaned on the board, a decrease in temperature of the water occurs. I'm glad I shortened C. Because if I had repeated myself, I would have run out of space. I just have just enough time. Just enough space. So H is 0. Then we have K left. H is 0, the amount of time that elapses before it starts. Actually, I have to say the water. The water starts to cool. Right away it starts to cool. I'm sure you know that from experience. All right, we'll extend the page, but only a teeny weeny bit. All right, and K, which is 20, represents the room temperature, or the temperature of the air. The temperature of the air in the room. Ah! Boy, it is really picky if you lean on the board even slightly. sorry, I have to get rid of that line. I'll just get rid of the whole thing. We'll write it again. 20, which represents the temperature of the air in the room. This board is mocking me. I must be tired. It just doesn't like the letter T. Done. I'll scroll it up a bit so you can see. Done. Okay. All right, there we are. All right, and so feel free to pause to take notes. This is one for you. All right, and so you're going to do something very, very similar. Think about what if it says half-life, all right, what that might be in terms of your equation. Radioactive element, mercurium, is used in household smoke detectors. Has a half-life of 432 years. The average smoke detector contains 20, I don't know what that symbol is for. Micrograms? I think micrograms of americonium-241. All right, so do this on paper, the A and the B, and I will check your work. All right, and then I won't read this. You can read this. All right, and so here are some key ideas about transformations of functions. All right, and so that ends this lesson. Our next lesson will be solving exponential equations. All right, bye for now.